in 3.1, we learned the formal definition for the derivative, and then we practiced using it lots. And while we were practicing, we had to remember all those old rules about how to simplify limits when you have 0 over 0. And I made you practice them. Well, the good news is that over the many, many, many years, millions and millions of mathematicians have used that formal definition to find the derivatives of functions, of all different kinds of functions. And we've noticed patterns that we can use. So if you understand the patterns well, then you don't have to go through that process every time. You still need to know that formal definition and have the ability to pull it out and use it when you're asked to. And you'll be asked to, in my class, you'll be asked to on the AP test. But the good news is, most of the time, like for daily use, we're going to talk about these, I'll call them shortcuts that you can use to find derivatives. So let's start with some basic ones. The derivative of a constant function. If you think of the graph of a constant function, which should have been the first page in your functions booklet, right? It's a horizontal graph. And if a derivative is slope, and the slope of a horizontal graph is 0, then the derivative of any constant must be 0. So that's our first rule. So here's an example. What if I told you f of x was 5? What's f prime of x? 0. The derivative of any constant is 0. So what's the derivative of 17? 0. What's the derivative of 1/3? What's the derivative of pi? Also 0. Okay, so I'm going to sneak one in here. I didn't give it a rule number. It's sort of an in-between rule. We're going to talk about another rule later that you can use to combine. But I want you to think about this because I want you thinking about slope. If derivative is slope, then any function that is linear, y equals mx plus b, we know how to find the slope of a linear function. It's this number that multiplies x. So if I give you a function y equals 8x minus 9, what's the derivative? Well, this is a linear function. The derivative must be the slope. The derivative would be 8. And if I said y equals negative 3/5 x minus 21, what's the derivative? Well, y prime is going to be the slope of this line. This is a linear function. Y prime will be negative 3/5. I notice here that in this example I used f of x notation, and in this example I used y notation. But remember, we can use both of those notations and still talk about the derivative. So the derivative of f of x is f prime of x. The derivative of y, you could denote y prime, or you could denote dy dx. They are both totally correct. So in the case where y equals negative 3/5 x minus 21, y prime equals negative 3/5. I could just as easily have written dy dx equals negative 3/5. The two notations mean the same thing. I just remembered I had that in a fancy slide. So same thing, here you go, in a fancy slide. The derivative of a constant is 0. What about, I'm going to think about functions where x gets raised to an exponent. So x squared, x cubed, x to the 4th. And I want you to think about this. Remember the triangle? The triangle comes back. So I'm going to use the formal definition to find the derivative of x squared. We've done that before. We get 2x. I could keep going. I could use that formal definition of the derivative to find the derivative of x cubed. I'm here. We did that one back in 3.1, so I have to take x plus h and multiply it out. And we get 3x squared. I could keep going, because that's what the greedy triangle would do. I could take the derivative of x to the 4th. I'd have to multiply out x plus h to the 4th. Maybe if you remember Pascal's triangle, you can use that as a shortcut to help you with this expansion. But no matter how you do your expanding, when everything sorts out, see what I've got highlighted in yellow here? That's the term that always pops out at the end. All the other terms, like the x to the 4th, cancel. You see I've crossed them out with a green line. And all the other terms that are left have an h in them, so they go towards 0. And it's like this first, not the first, it's this second term in that ends up being the derivative, which is pretty cool. You could think about doing it forever and ever, and you might notice a pattern. Derivative of x squared is 2x. The derivative of x cubed is 3x squared. The derivative of x to the fourth is 4x cubed. And we arrive at what we call the power rule. If I want to take the derivative of x raised to the nth power, it's like that n exponent comes down to the front and becomes a multiplier, and the new exponent is 1 less. So I want to talk about this example first. This is the most common way you're going to see the power rule. If I want to take the derivative of x to the fifth, that 5 comes down to the front, becomes a multiplier, and I end with 5x to the, my new exponent is 1 less than the old exponent. So that 5 dropped down to the front, my new exponent is 1 less, which is 4. So if f of x equals x to the fifth, then f prime of x equals 5x to the fourth. So in your book, they split up this power rule into 3 different parts. But here's the important part. If you can write your function as x raised to an exponent, it doesn't matter how weird or unexpected that exponent is, you can use the power rule. So I can use the power rule as long as I remember my algebra 2, which is going to be critical to your success here. As long as I remember that I can rewrite 1 over x to the fourth as x to the negative 4. Let me get this fixed up. There we go. So I can use the power rule to take the derivative of 1 over x to the fourth, even though we don't know anything about taking derivatives of fractions yet. If I can think about this as x to the negative 4th power, now I've written my function g as x raised to an exponent, and I can use the power rule. The negative 4 comes down to the front to multiply, and my new exponent is 1 less. If I was going to make any suggestion to you as you start your, you're going to take derivatives all semester long. And then just when you think we're not going to use derivatives anymore, you need them all second semester too. You're going to take a lot of derivatives in this class. So you're really happy that we're learning these shortcuts. But I'm going to tell you, if you don't get that algebra 2 idea in your head to rewrite this with a negative exponent, and you try to take the derivative of this using a rule we're going to learn about how to take derivatives of fractions, it takes at least 5 times as long. So please try to look for places where you can do this, because this next example is another place you can do it. I have x getting squared inside a radical, and that radical is taking the cube root. So remember that I can rewrite an expression like this using a fraction exponent with the index as the denominator in the fraction, and this exponent on x as the numerator. So instead of the cube root of x squared, I can write x to the 2/3. Once you do that, it's a pretty crazy function. You can take the derivative just by using the power rule. The 2/3 is going to come down to the front. I'm going to have x's left behind with an exponent that is 1 less than the original exponent. So in my head, I have to say 2/3 take away 1 makes negative 1/3. So that's a great answer, especially on the free response. If you're taking the multiple choice section, you need to be able to translate that back. So that's 2/3 x to a negative exponent means I'm going to have 1 over x to the regular exponent. So x to the positive version of the exponent. So x to the positive 1/3 means the cube root of x. So that's the same as 2 over 3 cube root of x. This is a multiple choice answer. This is totally fine on the free response section. Look at this next problem. I have a new function y equals 5 times x to the 7th. Well, if that were just plain old boring x to the 7th, I could use the power rule and I would be happy and there'd be no problem. So we need to know that this 5 here Oops. I don't even know what I did. That 5 there is what we call a constant multiplier. It's a number that's multiplying a function, some function that we already know how to take the derivative of. Well, I can hold the 5 for a second, like factor it out, take the derivative of x to the 7th, and then just multiply the 5 back together. So the derivative of 5x to the 7th is 5 times the derivative of x to the 7th. We talked about the last rule that the derivative of x to the 7th is 7x to the 6th. So my derivative is going to be 5 times 7x to the 6th, or 35x to the 6th. Here's another case where I have a chance to write my function using a negative exponent. So 4 over 5x cubed. I can think of factoring the 4/5 out. And then that x cubed in the denominator becomes x to the negative 3. Well, now 4/5 is a constant multiplier. So I'm going to hold it for a second. I'm going to take the derivative of x to the negative 3, which is negative 3 times x to the 1 less than negative 3, which is negative 4. Now the 4 and the 5 and then the 4/5 and the negative 3 can multiply together to make negative 12/5 x to the negative 4th, or negative 12 over 5x to the 4th. Okay, before I finish up, I just want to come back to this example here, the volume of a cube. So you will definitely be tested on the AP test and on your ability to use different letters besides x and y. Sometimes we get into a habit of just having y as a function of x or f of x as a function of x. So I think that if I had written on your paper y equals x cubed and I asked you to find y prime, or I asked you to find dy dx, after that little spiel on the power rule, I think everybody could do it. You're going to take the 3 down to the front. So y prime is going to be 3x squared. Just notice here, I have the same problem. I've just used different letters, so we have to start to get used to that. If I want to find the derivative of s cubed, where v is a function of x, so my derivative is going to be the derivative of v with respect to s. The 3 is going to come to the front. My new exponent on s is 2. So final answer.